Morrow County, Oregon. November 1891. The high desert plateau stretched beneath a slate sky, wind carrying the scent of sagebrush and coming snow. Thomas Birch stood between two crumbling stone walls, all that remained of an abandoned trading post, and drove his first stake into frozen ground. His neighbors gathered at a distance, shaking their heads. "Building in a graveyard of stone," muttered Frank Wheeler, whose own cabin sat a quarter-mile east. "Man's lost his mind." What they saw was failure. What Birch saw was 4,000 pounds of thermal mass, positioned perfectly to capture the winter sun. Before we reveal how this foolish decision would save Birch's life during the coldest winter in Oregon's recorded history, hit that like button and subscribe. And drop a comment telling us where you're watching from, because I'm going to show you a heating technique so effective, you'll wonder why modern builders forgot it. Subscribe now, and I promise you'll learn something that could cut your heating costs in half. The question wasn't whether Birch was crazy. The question was, what did this former railroad engineer understand about stone and heat that an entire settlement of experienced builders had missed? Thomas Birch arrived in Morrow County in late October 1891, riding a wagon loaded with tools, provisions, and a leather notebook filled with engineering calculations. He was 43 years old, recently widowed, and carrying knowledge that would soon divide a community. The ruins he'd chosen sat on a gentle south-facing slope. Two parallel stone walls, each roughly 30 feet long and 7 feet high, separated by 18 feet of empty space. They'd been built by a trading company in 1873, then abandoned when a railroad pushed through 5 miles north. Weather and vandals had claimed the roof and wooden components, leaving only sandstone walls, mortared with high-lime cement that had somehow survived 18 years of freeze-thaw cycles. "You'd do better starting fresh," advised Henry Gaskill, the settlement's most experienced builder. Gaskill had constructed 11 cabins in the region, all using green timber and conventional fireplaces. "Those walls are compromised. You'll spend more shoring them up than building new." Birch ran his hand along the weathered stone, feeling for cracks, testing joints with a thin blade. "These walls are exactly what I need," he said quietly. "For what?" Wheeler demanded. "A wind tunnel? That gap will funnel every gale straight through your living space." What they couldn't see, what Birch had calculated in his notebook during 3 weeks of observation, was that those walls represented stored solar energy. Sandstone has a thermal mass of roughly 0.2 BTU per pound per degree Fahrenheit. At 4,000 pounds per wall, positioned to capture low-angle winter sun from 11 in the morning until 3 in the afternoon, they would absorb and slowly release heat long into the night. "I'm not fighting the gap," Birch explained, his breath misting in the cold air. "I'm using it." The settlement's blacksmith, Otto Lang, shook his head. "German stonemasons don't build between ruins. They build fresh, square, proper. Scottish engineers," Birch replied, "build where physics makes sense." By mid-November, as Birch began constructing a low-profile cabin structure connecting the two stone walls, the mockery had spread through 3 neighboring settlements. Men would ride out specifically to watch the fool building in ruins, placing bets on how quickly winter would drive him out or kill him. What Thomas Birch understood, and what his critics dismissed, was a heating principle older than America itself: radiant thermal mass. In conventional frontier cabins of the 1890s, fireplaces were built against exterior walls, following European tradition. Heat from the fire traveled up and out through the chimney. Roughly 73% of generated warmth lost to the outside air. The remaining 27% heated the room through convection, hot air rising, cold air sinking, creating drafts and temperature stratification that left floors cold while ceilings scorched. Birch's design inverted this logic entirely. He built his firebox not against a wall, but in the center of the structure, equidistant from both ruins. The firebox itself was small, just 28 inches wide and 16 inches deep, but connected to a horizontal flue system that ran 18 feet in each direction, embedded directly into the base of the existing stone walls before venting through a small chimney at the north end. "You're heating the walls instead of the room?" Gaskill asked, watching birch mortar firebrick into place. That's backwards. Is it? Birch didn't look up from his work. Which retains heat longer, air or stone? The answer, of course, was stone. Air has a thermal mass of 0.018 BTU per cubic foot per degree Fahrenheit. Sandstone has 11 times that capacity. Once heated, the stone walls would radiate warmth for hours, potentially 12 to 14 hours after the fire died. But the settlement's self-appointed expert on masonry, a man named Douglas Bradley, who'd apprenticed in Philadelphia, declared the design primitive and inefficient. "You're creating a massive heat sink," Bradley announced to anyone who'd listen. "That stone will absorb your fire's heat, and you'll freeze while waiting for it to warm up." I've seen Russian stoves try this principle. They're folklore, not engineering. Bradley had never actually seen a Russian stove, nor did he understand the critical difference. Birch wasn't trying to heat stone to room temperature and stop. He was creating a thermal battery that would charge during the day with both fire and solar gain, then discharge slowly through the night. The physics were elegant. Both ruins faced south-southeast, angled to catch maximum low-winter sun. With proper glazing, which Birch was salvaging from the railroad's abandoned depot, the stone would pre-warm from 11 a.m. to 3 p.m. daily, absorbing roughly 380 BTU per square foot of exposed surface. His evening fire would then raise the stone's temperature another 20 to 30 degrees Fahrenheit, storing heat that would radiate inward through the night. Highland ignorance, Bradley called it, dismissing the entire concept to a gathering at Wheeler's cabin in early December. He'll burn through twice the wood trying to heat all that cold stone, and he'll still wake to frost on his blankets. What Bradley couldn't see, refused to see, was that Birch had insulated the exterior faces of both stone walls with a 12-inch layer of packed earth, clay, and straw. Heat would radiate inward, not outward. The stone wasn't a sink. It was a furnace. By December 15, 1891, Thomas Birch's structure stood complete, and the settlement's skepticism had hardened in a certainty of failure. The design violated every conventional wisdom of frontier architecture. His roof sat low, just 7 feet at the peak, creating a compressed interior volume of roughly 900 cubic feet instead of the typical 1,400. Claustrophobic, Wheeler called it. A man can't breathe in spaces that tight. But Birch knew that heating 900 cubic feet required 36% less energy than heating 1,400. Every BTU mattered. The walls themselves drew the harshest criticism. Rather than building traditional stud-and-plank construction, Birch had created a hybrid system. The existing stone ruins formed the long walls, while he'd closed the ends with double-wall construction, 2 layers of rough-sawn pine separated by 8 inches of dry sand. The sand, packed tight between the walls, acted as insulation with an R value of roughly 1.0 per inch. Sand? Gaskill had asked, watching Birch pour bucket after bucket into the wall cavities. "That'll settle and leave gaps." "Not if it's dry and well tamped," Birch replied. He'd demonstrated his technique, pouring 6 inches, tamping with a custom-made plunger, testing with a probe wire, then repeating. The process was tedious. It took him 4 days to fill both end walls, but when finished, the walls were solid, insulated barriers that wouldn't shift. The floor was perhaps his most controversial choice. Instead of laying planks directly on earth, as was standard, Birch had dug down 14 inches across the entire interior, then built up in layers. 6 inches of river cobbles for drainage and thermal mass, 2 inches of sand for leveling, 4 inches of compressed earth mixed with lime, and finally 2-inch pine planks laid tight. The cobbles alone weighed an estimated 3,800 pounds. "You've built a stone basement without walls," Otto Lang observed. "Winter frost will heave that floor into waves." But Birch had positioned the cobble layer below the frost line for the region, 13 inches deep, and the compressed earth lime mixture would cure into a rigid, moisture-resistant base. More importantly, that buried thermal mass would stabilize the interior temperature, preventing the dramatic day-night swings that plague conventional cabins. His window placement mystified everyone. Rather than the typical small opening scattered for light, Birch had installed 3 large salvaged windows, each 30 inches wide by 40 inches tall, all on the south wall, angled to maximize low winter sun penetration. The north wall had only one small window, 12 by 18 inches, positioned high for ventilation but minimal heat loss. Glass is the weakest point in any structure, Bradley lectured to a group of onlookers in late December. He's built heat bleed zones. Come January, he'll be stuffing those windows with straw to stop the drafts. What Bradley didn't understand was strategic solar gain. Those south windows, between 11 a.m. and 3 p.m. on clear winter days, would deliver approximately 2,000 BTU per hour directly onto the stone walls, pre-warming them before Birch lit his evening fire. On overcast days, he'd calculated he could cover them with hinged wooden shutters, insulated with wool batting, that he'd built into the window frames. The final element that drew mockery was his ventilation system. Birch had installed what he called a fresh air intake, a 4-inch diameter pipe that drew outside air from the north side, ran it beneath the floor through the warm cobble layer, then vented it into the firebox. Separate from this, a simple adjustable vent near the ceiling allowed moisture and cooking smoke to escape. He's pumping cold air into his own fire, Wheeler laughed. Probably read it in some European manual and doesn't understand it. But Birch understood perfectly. Cold outside air, pre-warmed to 40 or 50 degrees Fahrenheit by passing through the subfloor thermal mass, would feed his fire more efficiently than room temperature air while creating gentle positive pressure that prevented downdrafts. The system was self-regulating. The warmer the floor mass, the warmer the combustion air, the more efficient the burn. By Christmas week, 14 men had made the ride out to examine Birch's folly. Some came out of curiosity. Others came to witness what they assumed would be a spectacular failure once true winter arrived. Thomas Birch welcomed them all, offered coffee, and said nothing to defend his work. The design would speak for itself. He just needed winter to arrive. January 12, 1892, 4:47 a.m. The thermometer outside Frank Wheeler's cabin read 18 degrees below 0 Fahrenheit, negative 28 Celsius, the coldest temperature recorded in Morrow County history. Wheeler woke to frost coating the inside of his windows, his breath visible in the darkness of his own bedroom. He'd burned through 9 logs during the night, stoking his fireplace every 2 hours, and still his water bucket had frozen solid. The floor was so cold it burned his bare feet. A quarter-mile west, Thomas Birch slept under a single wool blanket. If you're watching this and wondering how that's possible, hit that like button and subscribe right now, because what happened over the next 72 hours would transform frontier building practices across 3 states. Comment below and tell us, what's the coldest temperature you've ever experienced? Let's see who's watching from the true cold country. The settlement woke to crisis that morning. Henry Gaskell's youngest daughter, barely 4 years old, was found with blue-tinged lips, early hypothermia despite sleeping between her parents. Otto Lang's wife wrapped herself in every blanket they owned and still shivered violently. Douglas Bradley burned through his entire weeks with supply in a single night, trying to maintain 50 degrees Fahrenheit inside his well-built, conventional cabin. At 8 a.m., Wheeler organized a group to check on Birch, certain they'd find him in distress, possibly frozen. They found him eating breakfast. The interior of Birch's cabin registered 68 degrees Fahrenheit, 20 degrees Celsius, measured on a mercury thermometer Wheeler had brought specifically to verify conditions. The stone walls radiated gentle, even warmth. No fire burned in the firebox. Birch had let it die at 11 p.m. the previous night, more than 9 hours earlier. Impossible, Bradley whispered, staring at the thermometer. But it wasn't impossible. It was physics. Birch's evening fire, burned from 6 p.m. to 11 p.m. using just 7 logs, had raised the temperature of 8,000 pounds of stone, both walls plus the floor cobbles, by approximately 30 degrees Fahrenheit. That represented roughly 48,000 BTU of stored thermal energy, now radiating inward at a rate of about 5,000 BTU per hour. In Wheeler's cabin, with its conventional fireplace, 73% of the fire's heat had escaped up the chimney. The remaining 27% heated air, which lost temperature quickly. His cabin was essentially a heat-through system. Stop burning wood, and within 2 hours, the interior temperature dropped below freezing. Birch's cabin was a battery. The stone absorbed heat slowly, but released it even more slowly. The thermal mass was discharging at roughly 1 degree Fahrenheit per hour. At that rate, even with outside temperatures at 18 below zero, the interior would remain above 50 degrees for at least another 12 hours without any additional fire. What did you burn? Gaskell asked, examining the firebox. How much wood? Birch walked to his neatly stacked wood pile and indicated a small section. 7 logs last night. I'll burn another 7 tonight. That's my daily consumption in deep cold. Wheeler did the math in his head. He'd burned 9 logs just trying to survive one night, and his family had still woken to frost. Birch was using 78 logs per week. Wheeler was burning through 90 logs every 3 days, more than 200 per week, and achieving inferior results. The difference was staggering. Birch was consuming roughly 35% of the wood his neighbors used, while maintaining superior comfort. The stone, Bradley said slowly, finally understanding. It's still warm from yesterday's sun. And the day before, Birch confirmed. And it'll still be warm tomorrow morning. Stone remembers heat. Air forgets it. The temperature outside would remain below zero for 3 consecutive days. A brutal cold snap that tested every structure in the settlement. Wheeler's family moved in with Gaskell, combining their fires and body heat just to stay safe. Bradley burned through 2 weeks of wood reserves in 72 hours. Otto Lang's chimney cracked from thermal stress when he overfired it in desperation. Thomas Birch burned 14 logs per day and maintained interior temperatures between 64 and 69 degrees Fahrenheit, never once feeling uncomfortable. On the morning of January 15th, when temperatures finally rose above zero, 7 men stood outside Birch's cabin, studying the structure with new eyes. The mockery had ended. The education was beginning. By late January 1892, Thomas Birch's cabin had become a laboratory, and the entire settlement had become students. Henry Gaskell arrived on January 24th with a proposal. Let us measure everything. Record it properly. I want to understand exactly what you've achieved here. Over the next 2 weeks, a systematic comparison was conducted between Birch's thermal mass design and 3 conventional cabins of similar size. The results were documented in Gaskell's meticulous handwriting, numbers that would later be referenced in regional building guides. Test period, February 1st to 14th, 1892, average exterior temperature, 12 degrees Fahrenheit minus 11 degrees Celsius lowest recorded temperature, minus 4 degrees Fahrenheit minus 20 degrees Celsius Birch's cabin. Interior temperature range, 62 to 71 degrees Fahrenheit, 17 to 22 degrees Celsius. Daily wood consumption, 11 logs. Average 4.5 inches diameter, 16 inches length. Fire duration, 5 to 6 hours per day. Evening only. Heat retention after fire dies, 12 to 14 hours maintaining 60 degrees Fahrenheit or above total weekly wood consumption. 77 logs Wheeler's cabin, conventional fireplace. External wall, interior temperature. Range, 38 to 67 degrees Fahrenheit, 3 to 19 degrees Celsius. Daily wood consumption, 28 logs, same dimensions. Fire duration, 18 to 20 hours per day, nearly continuous. Heat retention after fire dies, less than 2 hours above 50 degrees Fahrenheit. Total weekly wood consumption, 196 logs Bradley's cabin, conventional fireplace. Masonry chimney interior temperature range, 42 to 65 degrees Fahrenheit, 6 to 18 degrees Celsius. Daily wood consumption, 24 logs fire duration, 16 to 18 hours per day. Heat retention after fire dies, approximately 3 hours above 50 degrees Fahrenheit. Total weekly wood consumption, 168 logs. The numbers told an irrefutable story. Birch was using 39% of Wheeler's wood while maintaining superior comfort. Even compared to Bradley's well-built cabin with its expensive masonry chimney, Birch achieved 46% greater fuel efficiency. But the most remarkable measurement came during a controlled test on February 9th. At 6 p.m., with exterior temperature at 8 degrees Fahrenheit minus 13 degrees Celsius, Birch lit his evening fire using precisely measured fuel, 8 logs of seasoned pine. The fire burned steadily until 11 p.m., 5 hours total. At 11 p.m., the interior temperature measured 71 degrees Fahrenheit, 22 degrees Celsius, and Birch closed the firebox damper completely, letting the fire die. Gaskell, Wheeler, and Bradley remained in the cabin through the night, recording temperature every hour. 11 p.m., 71 degrees Fahrenheit, fire out. 12 a.m., 69 degrees Fahrenheit, 1 a.m., 68 degrees Fahrenheit, 2 a.m., 67 degrees Fahrenheit, 3 a.m., 66 degrees Fahrenheit, 4 a.m., 65 degrees Fahrenheit, 5 a.m., 64 degrees Fahrenheit, 6 a.m., 63 degrees Fahrenheit, 7 a.m., 62 degrees Fahrenheit, 8 a.m., 61 degrees Fahrenheit, 9 a.m., 61 degrees Fahrenheit. Sun begins warming south wall. 10 a.m., 62 degrees Fahrenheit. Solar gain begins. The stone walls were still radiating stored heat 13 hours after the fire had died, and solar gain through the south windows was beginning to recharge the system. On clear days, Birch often didn't need to light a fire until after sunset, as passive solar heating maintained interior temperatures in the mid-60s Fahrenheit. It's not one system, Birch explained to the group gathered in his cabin that morning. It's 3 working together. The stone stores heat from the fire. The floor mass stabilizes temperature swings. The south windows capture solar energy. Each supports the others. Douglas Bradley, who had been the loudest critic, stood and examined the stone wall, running his hand across the warm surface. "I called this primitive," he said quietly. "I was wrong. This is more sophisticated than anything I learned in Philadelphia." Otto Lang conducted his own test, measuring the temperature gradient from floor to ceiling in both Birch's cabin and his own. In Lang's conventional cabin, the floor measured 41 degrees Fahrenheit, while the ceiling reached 68 degrees Fahrenheit, a 27-degree stratification that wasted heat and left occupants' feet frozen while their heads sweated. In Birch's cabin, the floor measured 64 degrees Fahrenheit and the ceiling 67 degrees Fahrenheit, just 3 degrees of variation, indicating even heat distribution. The thermal mass wasn't just storing heat, it was radiating it evenly from all sides, creating what Birch called enveloping warmth rather than the directional blast of a fireplace. By mid-February, the settlement had witnessed enough. Frank Wheeler made the announcement that would change frontier architecture in the region. "We're rebuilding the community hall using Birch's principles. Anyone who wants to learn the technique, come help." The stone walls Thomas Birch had salvaged from ruins, walls his neighbors had called worthless, had proven to be the most valuable building material in Morrow County. Spring 1892 brought transformation to the high desert plateau of Oregon. By late March, as snow melted and revealed muddy ground, 7 construction projects had begun, each incorporating thermal mass heating principles. Frank Wheeler was building a new cabin with stone walls positioned to capture southern sun. Henry Gaskell was retrofitting his existing structure, adding a heat-retaining stone mass behind his fireplace. Even Douglas Bradley was designing a community building with a central firebox and radiant stone walls. But the most dramatic adoption came from an unexpected source. The Umatilla people, whose reservation bordered the settlement to the east, had watched Birch's construction with interest. In April 1892, a delegation led by a man named Clarence Burke visited Birch's cabin, examined the design, and asked detailed questions about the horizontal flue system and stone positioning. "Our grandmothers built earth lodges with fire pits that kept us warm all night," Burke explained through an interpreter. "Your stone walls work like the earth. They remember the heat. This is not new wisdom. This is old wisdom, built with new materials." Birch listened carefully, then asked Burke to explain the earth lodge design. What he learned humbled him. Indigenous builders had understood thermal mass for generations, using compacted earth walls 2 to 3 feet thick that absorbed daytime heat and radiated it through cold nights. Birch hadn't invented a new principle. He'd rediscovered an ancient one using different materials. By late 1893, the technique had spread beyond Morrow County. A rancher named Samuel Coffin built a stone mast barn that kept his cattle warm through winter, reducing feed costs by an estimated 30% because the animals burned less energy maintaining body temperature. A schoolteacher in Heppner, Oregon, convinced the town council to build a new schoolhouse using birch's design, creating a warm learning environment that used 60% less wood than the old building. Regional newspapers began covering what they called the Oregon Stone Method. An article in the East Oregonian dated November 1893 described Birch's cabin and included rough diagrams, spreading the knowledge to builders across the Pacific Northwest. The most comprehensive adoption occurred in Grant County, where a devastating winter in 1894-95 killed 3 homesteaders who ran out of firewood. In response, the county surveyor, a man named William Chandler, studied Birch's design and created standardized plans for thermal mass cabins that were distributed free to new settlers. Between 1895 and 1900, at least 43 cabins in Grant County incorporated stone mass heating, and the winter mortality rate dropped to 0. Thomas Birch himself lived in his cabin until 1907, when he was 59 years old. In 15 winters, he never once experienced inadequate heat, never ran out of firewood, never faced the life-threatening cold that plagued conventional cabins. His daily wood consumption remained consistent: 11 to 14 logs in the coldest weather, 7 to 9 logs in moderate winter conditions. When he finally sold the property to move closer to his daughter in Portland, the new owner, a young homesteader named Robert Mackenzie, wrote in his journal, "Purchase the Birch place today. The stone walls are as solid as the day they were built, still warm to the touch on winter mornings. I have never seen construction so sensible. Before we close, I need you to do 3 things. First, hit that like button if you learned something that could actually save you money and keep you warmer. Second, subscribe to this channel because we're uncovering more lost frontier wisdom every week, techniques that modern builders forgot, but you can use today. And third, comment below and tell us, would you build a thermal mass cabin or do you prefer modern heating? I want to hear from everyone watching, from Alaska to Australia. The thermal mass cabin at Morrow County still stands today, though it's been modified and expanded over 130 years. The original stone walls, those worthless ruins that neighbors mocked in 1891, remain the structural core, still radiating stored heat on winter nights, still proving that Thomas Birch understood something fundamental that his critics had missed. It wasn't that he was smarter than the experienced builders who mocked him. It was that he was willing to see value where others saw failure, to trust physics over convention, to learn from stones that had outlasted the men who first laid them. The neighbors laughed when he built between 2 ruins. But those ruins and the wisdom Birch extracted from them outlasted all the laughter, all the criticism, all the conventional cabins that have long since rotted away. Stone remembers, stone endures, and stone, when understood properly, keeps you warm. This narrative is based on documented frontier building techniques and thermal mass principles used in the American West during the late 19th century. While specific characters and dates are dramatized for storytelling purposes, the physics, measurements, and construction methods described are accurate to historical practices. This content is educational and historical in nature and should not replace modern building codes or professional engineering consultation.